Hi everybody, I'm Greg Fishel. Welcome to bonus weather video number 1 for this week as we play catch up. And we're going to be talking about something called the electromagnetic spectrum today, which is a fancy phrase for the description of everything that is flying by us at any one given moment in our lives. If we could see everything that was passing by us at any one given second, it would be totally overwhelming. Fortunately, the human eye can only detect a very, very small portion of that spectrum so as to avoid us getting overloaded with input, I guess. So let me put myself down here in the corner, and I want to credit the University Center for Atmospheric Research, or UCAR, located out in Boulder, Colorado. They generated this graphic, and I thought it was pretty cool, so I wanted to share it with you. But this is basically the entire spectrum, all the wavelengths and frequencies of everything that flies through the air, ranging from radio waves, which have very, very long wavelengths, to microwaves, to infrared radiation, to visible radiation, which of course is the part of the spectrum that we see. And then you have ultraviolet and X-ray and gamma ray. And so you can see the wavelengths here going from very, very long. And the wavelength is defined as the distance from the crest of a wave to the next crest. Or you can look at it from the base of the wave to the next base. But basically, that is the wavelength, and it gets shorter and shorter and shorter as you get up into the ultraviolet, X-ray, and gamma ray. And in terms of the size, here are the things that those wavelengths would be commensurate with, such as buildings, human beings, honeybees, all the way down to molecules and atoms and atomic nuclei, which obviously is very, very, very small. And what is really interesting, at the very bottom there, you see the temperature of the bodies emitting any particular wavelength, and it goes all the way up to 10 million degrees Kelvin, okay? So get pretty hot at those very, very short wavelengths. Now, I thought it might be interesting to talk about what parts of the spectrum are weather related, okay? Well, ultraviolet radiation from the sun is absorbed by the Earth's surface, and so obviously that is our ultimate source of warmth, if you will, although the atmosphere doesn't really absorb all that much of that incoming solar radiation. It's absorbed by the ground, then the ground re-radiates it in the infrared, and that is what goes into heating the atmosphere from the ground up. Visible light obviously allows us to see everything, like the sky and the clouds and rainbows and all that type of thing. And then infrared radiation is radiation emitted by the Earth. Now, a portion of that escapes to space, while other portions are absorbed by gases and returned to the Earth. And were it not, and this is what we call the greenhouse effect, and if it wasn't for the natural greenhouse effect, we wouldn't be alive right now, okay? It makes a difference of the Earth's average temperature of 60 degrees Fahrenheit, okay? Gases like water vapor, carbon dioxide, nitrous oxide, methane, all of those gases, even though they occupy a very small part of the atmosphere, will literally make the difference between life and death on this planet. So a small thing can have a very, very big effect. Now, in terms of data collection, what sort of wavelengths are involved here? Well, every day, twice a day, weather balloons are launched all over the world, and they travel upwards, and then they have a radio transmitter which then transmits that data back down to the ground so that we can make use of it. So the radio waves have much, much longer wavelengths, but that's how that data is transmitted from the radiosonde all the way back down to the ground. Satellite measurements make use of, I believe it's 16 different channels, and it goes all the way from 0.47 microns. Now, a micron is 10 to the minus 6th meters, okay? So if you had 1 micron, you would start off with the number 1, and then you would move the decimal point back 6, okay? So I guess you would have 5 zeros and a 1, okay? And that would be 1 micron. And then it goes all the way up to 13.3. Now, the visible range is about 0.4 microns to 0.7 microns, okay? So when you see a visible satellite picture, that means that you're looking at the part of the spectrum which allows the human eyes to see things, okay? But obviously at night, when it gets dark, you can't see anything anymore. And so we have to rely on infrared radiation to tell us where the clouds are, because the satellite can measure how much infrared radiation the tops of the clouds are emitting, and then we can convert that into a temperature, and we know how the temperature varies through the atmosphere at different elevations, and so we can make an assessment as to how high that cloud is based on the temperature, which we get from the amount of infrared radiation that it is emitting. Okay, so that's a very, very useful process. And then radar measurements are basically, the radar itself is transmitting data in the microwave range, which is our wavelengths of about 5 to 10 centimeters. And I think we've talked about this before, where most television station radars are 5-centimeter radars, which are fine, except they tend to do what we call attenuate when they have to go through areas of heavy precipitation. So if you had one thunderstorm here and another one right behind it, the 5-centimeter radar would have a hard time getting through the first one to see the second one, whereas a 10-centimeter radar is more efficient at doing that. And that's what all the National Weather Service Doppler radars are operating at, that wavelength of 10 centimeters. So there were lots of times when I was in the television business where our radar, which was a 5-centimeter, would do just fine in normal situations, but if we had a whole bunch of strong to severe thunderstorms and it was trying to poke through one to see another one on the other side, honestly, it didn't do a very good job of doing that. And so we would then, use the National Weather Service radar as a complement, C-O-M-P-L-E-M-E-N-T, okay? Not a competitor, but a complement to what our radar was showing. And when you combine the two, it gave you a really good picture as to what was going on. So that's just a little bit of an introduction as to all the different wavelengths within the spectrum and how some of that is related to weather and also related to weather data collection. The next bonus weather video, which will be coming out this evening, will be taking a look at something called the Earth's radiation budget, okay? In other words, there has to be about the same coming in as there is going out in order to keep the Earth's average temperature relatively constant. So we'll take a look at all the different processes that are involved in stuff coming in and stuff going out. That's the second bonus weather video of the day, which will be available very, very shortly. All right, folks, that's it for now. You all have a great rest of your Wednesday evening, and we'll talk to you soon. See you later.